Hello everyone, welcome to this lecture. In the previous lecture, we studied characteristics of FRFs of single degree of freedom systems. In this lecture, we are going to study characteristics of FRFs of multi-degree of freedom systems. Let me give a brief outline of the lecture first. First, we will define FRFs and inverse FRFs for a multi-degree of freedom system. Then we will look at the characteristics of FRFs of a multi-degree of freedom undamped system, where we will first derive a relationship between the FRF and the model. Then we will define anti-resonances. We will look at anti-resonances for a point and transfer FRF. We will look at why anti-resonances occur and how to estimate anti-resonances. Then we will look at the FRF characteristics for multi-degree of freedom damped systems. Okay. So therefore, the topic today is characteristics of FRFs of multi-degree of freedom systems. Okay. So let us first of all define the FRF for a multi-degree of freedom system, right? So if the system has MDOF, then the system will have FRF matrix, right, of size n by m. Okay. And so similar to the receptance, mobility and inertance we defined for a single degree of freedom system, we will have a receptance FRF matrix, mobility matrix, inertance matrix. So let us define a particular FRF receptance FRF alpha jk. Alpha jk is nothing but the ratio of the displacement amplitude, okay, at j degree of freedom in the frequency domain and the force amplitude at the k degree of freedom in the frequency domain. So we can write this as xj omega divided by fk omega, and no forces being applied at rest of the degrees of freedom. So fq is equal to 0 for all q except q is equal to k. So except k degree of freedom, no force is applied at the remaining degrees of freedom, and the force being applied is a harmonic force. So this is nothing but the frequency response function for a multi-degree of freedom system. So if we are interested to know the mobility of corresponding mobility of RF, then we just need to multiply this alpha jk by I omega. That will give us the mobility of RF, and if we multiply further it by I omega, we will get the inertance of RF. Let us now try to define inverse FRF. Okay. So similar to a single degree of freedom system, we can have inverse FRFs like dynamic stiffness, right, or impedance or apparent mass, right. So let us define the dynamic stiffness. So here again we will have dynamic stiffness matrix instead of just one dynamic stiffness that was there for a single degree of freedom system. Right. And if we define, say, one of the elements of the stiffness matrix, dynamic stiffness matrix, say zjk, then that is nothing but the ratio of the force amplitude at the j degree of freedom in the frequency domain and the displacement amplitude at the k degree of freedom in the frequency domain. So this is nothing but fj omega divided by xk omega, and with the displacement at all the other degrees of freedom being constrained, okay, all the remaining degrees of freedom. So we also need to have a condition that xq is equal to 0 for all q except q is equal to k. Okay. So this is basically these are the conditions to be satisfied at all the rest of the degrees of freedom to determine the dynamic stiffness. So it is easy to see that here, that because the conditions to be satisfied at all the other degrees of freedom, okay, being different for the FRF and the dynamic stiffness. These elements, they are not inverse of each other, right. The dynamic stiffness is not reciprocal of the corresponding FRF term. So, ZJK omega is not equal to inverse of alpha JK omega, correct. That has to be kept in mind. So, for a single degree of freedom system this was valid, but for a multi degree of freedom system this is not valid. However, the alpha can be written as inverse of the dynamic stiffness matrix. So, that inverse relationship exists at the matrix level, not at the individual element level for the two matrices. Let us go to next page. Another thing we note from the practice that frequency response functions, they are the preferred quantities of measurement as compared to the their corresponding inverse counterparts, like for example dynamic stiffness in this case. Okay. So, let us try to answer this question, that why FRFs are preferred quantities of measurement as compared to their inverse counterparts. Right. Let us try to answer this question, and let us try to explain it based on the frequency response function, receptance alpha jk and corresponding dynamic stiffness, which is zjk. So, let us take the example of a beam. So, let us say we have this beam, and let us say we have used say 4 points on this beam to describe its displacement profile, right. And let us say and then we have the displacement and slope at all these 4 points being the quantities of interest, right. So, we will have displacement and slope at these DOFs being the relevant degrees of freedom, and if we number them as say 1, say 2, 3, 4, 5, 6, 7 and 8. So, there are 8 DOFs, and let us now try to see that if we let us say wish to measure the frequency response function alpha 1 3, right, then what needs to be done. So, to measure alpha 1 3 we need to apply the force at the third degree of freedom, right. So, in this direction, and then measure the response at first degree of freedom, that is x1, and the forces at all the other degrees of freedom they need to be 0, and that is something very easy to satisfy, right. Not applying a force is very simple, we do not have to apply force, right. So, therefore, we can measure alpha 1 3 easily. Let us talk about now measurement of say Z13. If I am interested to measure the dynamic stiffness Z13, then what how that can be measured. So, to measure Z13 we need to have displacement at the third degree of freedom, right. So, we need to have displacement, we need to measure displacement at the third degree of freedom, we need to apply force at the first degree of freedom, right, and then we need to constrain all the remaining degrees of freedom, right. So, that is a requirement that is very difficult to satisfy in practice, constraining all the degrees of freedom other than the degree of freedom of interest, right, and hence it is very difficult to measure dynamic stiffness in practice, and that is why measuring the FRF is something preferred as compared to the inverse FRF measurement. Now, Now we would talk about the FRF characteristics of undamped multi-degree of freedom system. And for this, let us first of all derive the relationship between the frequency response functions and the model of the system, right. And this relationship, in fact, we have derived earlier in one of the lectures by finding the steady state response of the system to harmonic forces, and from there we have derived that relationship already. But here let us look at an alternative derivation to obtain that relationship, and for this particular method we are going to start from the relationship of the FRF with the spatial model of the system. Okay. So, now we are going to talk about relationship between the FRFs and model of the system, right. So, the model is available in the form of natural frequencies, right, and the mode shapes, mass normalized mode shapes of the system. So, these two quantities are there for an undamped system which make up the model, right. And if that is available, then how can we find the frequency response functions? So, that relationship we are going to derive essentially will give us that ability to determine the FRFs. So, we start from the relationship between the FRF and the spatial model, and we know that the frequency response function matrix is inverse of the dynamic stiffness matrix. Okay. And we can also write down this, if we take inverse of both sides, then we can also write down this as alpha inverse is equal to matrix Z, right. And the matrix Z for an undamped system is nothing but K minus omega square m, right. And now if we pre and post multiply by phi transpose and phi matrix, right, which is the matrix of mass normalized mode shapes, right. If we do that, then what is going to happen? We will have phi transpose alpha inverse phi, right, and then on the right hand side we will have phi transpose K phi minus omega square phi transpose m phi. Okay. And if we now use the orthogonality properties of the mass normalized mode shapes, then this matrix phi transpose K phi is simply the matrix of eigen values omega r square, a diagonal matrix of eigen values, and phi transpose m phi is simply a unity matrix, right. So, now if we take the inverse of both sides, right, if we take inverse of both sides, then what we get? We get phi inverse alpha phi inverse transpose, right. So, and then we have here this would be a matrix of minus omega r square minus omega square diagonal matrix and inverse of this, correct. So, on the left hand side we have used the result from the matrix algebra, that inverse of A into B is equal to product of B inverse and A inverse. So, now if we pre and post multiply by phi and phi transpose, right, then the on the left hand side we will be left only with the FRF matrix. Okay. So, let us write that on the next page. So, if we multiply by pre and post multiply by phi and phi transpose. Okay. So, that gives us alpha matrix into phi omega r square minus omega square inverse and phi transpose. So, this in fact we get the relationship between the FRF matrix and the modal model. So, on the right hand side we have the modal quantities, the natural frequencies omega r square omega r and mode shapes given by the mass normalized mode shape matrix phi. We can also write the right hand side as a sum of terms, right, from r is equal to 1 to n, right, and that we can write as phi. So, that is the rth mode shape multiplied by phi r transpose divided by omega r square minus omega square, right. So, as a series we can write down series sum. And now if we are interested to know a particular FRF, say alpha j k, then that can be extracted from this simply as phi jth element of the rth mode multiplied by the kth element of the rth mode divided by omega r square minus omega square. So, this is in fact the relationship between the modal and the frequency response function, right. And this is the same, in fact the same relationship we derived earlier in one of the previous lectures, right, based on the response of the system to harmonic forces. So, this quantity phi j r and phi k r, this quantity is often referred as modal constant, right. So, this numerator is referred as modal constant. Okay. Let us talk about another important characteristics of multi-degree of freedom FRFs, that is anti-resonances. Okay. And let us take example of one of the FRFs of multi-degree of freedom system, right, to see what anti-resonances are. And let me take the example of a receptance FRF alpha 1 1, right. So, this is the receptance FRF, right, and this is basically a point FRF. In this case, this is a point FRF. So, if we look at any FRF alpha j k, right, and if j is equal to k, right. So, all such FRFs are referred as point FRFs, right, or direct FRFs or driving point FRFs. So, there are several names which are used to indicate or refer to these FRFs, driving point FRF. Okay. And if degree of freedom j and k are different, right. So, FRF is taken at degrees of freedom in which the excitation and the response is at different degrees of freedom, then all such FRFs are referred as cross FRFs or transfer FRFs. Okay. So, in the present case we are basically talking about a point FRF, and let me take the example of a 3 degree of freedom system, right, example of a 3 degree of freedom system for the purpose of discussion. Okay. So, so for this 3 degree of freedom system, the FRF alpha 1 1 may look something like this. So, here I am plotting the alpha 1 1 magnitude, right, magnitude of alpha 1 1 in decibels, and on this axis we are plotting the frequency omega. So, so this FRF may look something like this. Okay. So, this is typically how a point FRF would look like, right. And if I also plot the phase of this, then if I plot here now the phase of alpha 1 1 omega, right. So, in degrees, okay. So, here I have the frequency axis, and now this phase is going to may look something like this. It is an undamped system. So, phase is 0, right, before resonance frequency, and then we have the phase building up here like this, then again going down here, and again it builds up, again it reduces, and again it builds up like this. So, this is basically the phase plot of this particular FRF. So, what we observe from these plots, right. So, the first thing we observe is that we have now these 3 peaks in the FRF. There are there are 3 peaks in the FRF, right, which basically represent the resonant frequencies of the system, right. So, because there are 3 modes of vibration of this 3D graph freedom system, and then there are 3 corresponding natural frequencies. So, these peaks basically are occurring at the natural frequencies, wherever the excitation coincides with the natural frequency, at that time the response is very high. So, these 3 peaks are there, and the amplitude here for for an undamped system, it it will be theoretically infinity, right, but for a practical system you will have very high amplitude, right. And then we also see there are frequencies where the response is very low, right. So, there are frequencies where the FRF magnitude is very low, right. In fact, we will see that for undamped system this FRF magnitude at these frequencies is in fact 0, right. So, if you look at this frequency, at this frequency and at this frequency, right, the FRF magnitude is 0. So, at these frequencies we see that the FRF magnitude is very low, right, and the shape of the FRF curve looks like inverted peak at these frequencies, right, and that is why these frequencies are referred as anti-resonant frequencies. So, these frequencies they are referred as anti-resonant frequencies, okay, and these values we get, right, we refer to them as anti-resonances. So, therefore, these are the anti-resonances, so this and this, right, they are anti-resonances, right, and we can call these as resonances. So, another important fact about anti-resonance frequencies is that if we have, let us say, the frequency response function alpha j k, right, and now if any force acts at the kth degree of freedom, okay, and the frequency of the force is equal to the one of the anti-resonant frequencies of this particular FRF, then the response at the jth degree of freedom would be 0. okay, if assuming the system to be undamped, or at least the response will be very small at that degree of freedom. So, that is in fact one of the important aspects of anti-resonance frequencies. Now, the question arises that why anti-resonance frequencies occur, right? Why do anti-resonances occur? Let us try to answer this question now. Let us take the example again of the point FRF, and to understand the occurrence of anti-resonances, let us look at what are called as modal contributions. So, let us take point FRF of the 3 degree of freedom example we have taken, alpha 1 1, and this point FRF alpha 1 1 omega for the 3 degree of freedom system can be written as sum of phi 1 r phi 1 r, right, divided by omega r square minus omega square with r varying from 1 to n, right. Now, we can expand this as phi 1 1 phi 1 1 upon omega 1 square minus omega square plus phi 1 2 phi 1 2 upon omega 2 square minus omega square plus phi 1 3 phi 1 3 omega 3 square minus omega square, isn't it? So, therefore, what we see the FRF is contributed by 3 terms, and each term, if we focus our attention, then each term is dependent on modal properties of only a particular mode. For example, if we look at this first term, then this first term depends on the on the first element of the first mode shape and first natural frequency, right. So, it means this term is completely determined by the first mode of vibration, and that is why this is referred as contribution of the first mode to the frequency response function, and we refer this as mode 1 contribution. Similarly, if we look at the second term, that depends on the first element of the second mode shape and the second natural frequencies, and therefore, this particular term basically tells us or indicates the mode 2 contribution to the frequency response function, and the third term represents mode 3 contribution to the frequency response function, right. So, these basically are also referred as modal contributions, right, contributions of different modes to the frequency response function. And now, the frequency response function, therefore, magnitude is determined by how these modal contributions combine, right, depending upon the sign of each modal constant or each modal contribution, they would be added or subtracted, right. And for a undamped system, the modes are real, right, and that is why these modal contributions either have positive sign or negative sign, and that would determine that how these modal contributions combine and make up the FRF magnitude. So, let us draw these modal contributions for this FRF in order to get further insight into the modal contributions, and then we will further see that how anti-resonances occur based on that. So, let us plot the FRF magnitude alpha 1 1, right. So, this is the FRF magnitude in dB versus frequency, and let us first of all plot the FRF itself in dB, and this is may look something like this. Okay. Let us now plot let us plot modal contribution 1 mode 1 contribution, right. So, let us plot mode 1 contribution, and that contribution would look something like this. That is mode 1 contribution. Okay. Then let us plot mode 2 contribution. Mode 2 contribution, if you plot, it would look something like this. And then plot mode 3 contribution. Like that. Okay. So let me also write down that this is mode 3 contribution. Then I have mode 2 contribution, and then I have this rate curve indicating mode 1 contribution. So what we note is that if I look at, let us say, mode 1 contribution, then the mode 1 contribution is maximum when the frequency of excitation coincides with the natural frequency of mode 1, and as the frequency of excitation goes away from the mode 1 natural frequency, the modal contribution of mode 1 also proportionately reduces, right, it also reduces. And same thing can be said about the mode 2 and mode 3 contribution. So that is one clear characteristics of modal contributions, that the contribution of a particular mode is maximum when in the frequency range which covers the natural frequency of that mode, and as we go away from that range, the contribution of that mode reduces. Let us plot below this now the sign of the modal contributions, right, because sign of these modal contributions would determine that how these modal contributions combine and they generate the FRF magnitude, right. So let us plot the sign of the modal contributions here, and let us now the sign of mode 1 contribution when omega is less than the natural frequency of mode 1, right, then the sign of that modal contribution is positive, right, because the denominator is positive. If we look at the modal contribution expression, then we see that for the point FRF, the numerators, they are all positives, right, while the denominator sign depends on whether the frequency of excitation omega is more than or less than the natural frequency of that mode. So therefore, if I plot this sign of this here, and let us first of all also represent the natural frequencies of these modes here, right. So this is first natural frequency m1, then I have this second natural frequency omega 2, then this is the natural frequency of third mode omega 3, right. And so now we can plot the sign. So let us say this is positive sign, right, and then what happens, the sign changes as soon as the frequency becomes more than the natural frequency of mode 1, right. So this is positive here, so let me write that here, that is positive sign, and this is negative sign. And now let us draw the sign of, let us mark the sign of now mode 2 contribution. Now mode 2 contribution, let us say again this is positive till omega is less than omega 2, and then the sign changes like this, right, and then we have negative sign when omega is more than omega 2. Let us also plot the sign of mode 3 contribution, that is positive when omega is less than omega 3, right, and when the omega exceeds omega 3, right, then what happens, the sign becomes negative. So these plots basically indicate to us the signs of various modal contributions. So let us look at the frequency range between mode 1 and mode 2. that is when omega is less than omega 2 and more than omega 1. So, what are the signs of various modal contributions? We see that mode 2 and mode 3 contributions, right, they have a positive sign, while mode 1 contribution is negative, right, it has a negative sign as shown by the red line, right. And therefore, what happens at some frequency in this range, these contributions, the positive and negative contributions, they would mutually cancel. So, at that frequency, the FRF magnitude would be 0, and that frequency forms an anti-resonance frequency of this system, right. Similarly, if we look at the frequency range in which omega is less than omega 3 but more than omega 2. So, here what we notice, we see that mode 3 contribution is positive, right, and mode 1 and mode 2 contributions, they are negative, right. So, at some frequency in this range, these contributions would cancel each other, right, and at that frequency the FRF magnitude would be 0, giving rise to an anti-resonance frequency, or anti-resonance at that frequency. So, therefore, for a point FRF, what we see is that between every two consecutive peaks or resonances, an anti-resonance frequency exists, an anti-resonance exists, right. So, this is for a point FRF, this is for a point FRF. Right, and this happens because we saw the FRF modal series that the numerators are always positive there, right. We are having the terms like 511, 511, that is 511 square. The second modal contribution is a numerator 512, 512, that is 512 square. So, numerators are always positive, and therefore, the sign of the modal contribution is determined only by the fact that whether the frequency of excitation is more than or less than the natural frequency of that mode. And therefore, the phenomena of mutual cancellation of different modal contributions, that is guaranteed to occur between every two successive peaks, and that is why you will have anti-resonance frequency between every two successive peaks in a point FRF. Let us now take a transfer FRF and see what happens there. Let us take a transfer FRF. So, for the 3 degree of freedom system, let us take receptance alpha 1 2, right, and let us again let us first of all sketch the FRF magnitude here. So, that FRF magnitude for this FRF may look something like this. Right. So, this is the FRF magnitude. So, in this FRF will have the resonance peaks at the same frequency, right, which occurred in the point FRF, because resonance frequencies will not change from FRF to FRF. And let us now also plot the signs of the modal contributions as we did for the point FRF. Okay. So, let us first of all plot the sign of the modal contribution for the mode 1. So, let me plot on this graph itself. So, that would be this. So, this will be positive sign for this one, and then we have negative sign after this. So, these signs I am plotting for a specific 3 degree of freedom system, right, and depending upon the parameters of the system, these plots would change. So, the signs I am plotting there for a specific system, a typical system, what we will have, right. And so, this is positive sign and this is negative sign, and then we have for the second mode, for this particular system we have positive sign before when the omega is less than omega n2 or omega 2, like this, and then we have for mode 3. So, for this particular system for which I am making the plot, the sign of the modal contribution is negative when omega is less than omega 3, okay. So, like this, and then it becomes positive when omega is more than omega 3, okay. So, let me also write down here, this is omega 1, this is omega 2 and this is omega 3, okay. Now, what we observe from here, let us look at the frequency range between omega 2 and omega 3, omega 2 and omega 1. So, here again we see that the mode 1 and mode 2, right, sorry, mode 1 and mode 3, they have negative contributions, okay, while mode 2 has positive contribution, right, and that is why we see that there is a frequency in this range where FRF magnitude has become 0, forming an anti-resonant frequency, right, as we see from here that at this frequency here there is 0 magnitude, right, and then anti-resonance frequency is there. But let us now look at the range omega, range where omega is less than omega 3 and more than omega 2. So, in this range all the modal contributions, mode 1, mode 2 and mode 3 all have negative contributions, right, and therefore, there is no frequency where mutual cancellation of these modal contributions may occur, right. And that is why what happens, these contributions, they reach only to the total contribution reach to some minimum value in this range, forming a minima in this range, right. So, there is no anti-resonance frequency, but a minima occurs. For example, at this frequency here, right, at this frequency we have a minima, okay. So, in a transfer FRF, the sign of the numerator also plays a role, because it is no longer always positive. And that is why in this particular example it is seen that for mode 3 contribution, the sign of the the modal sign of the modal constant or the numerator is different, it is not positive, right. That is why it has led to a negative contribution when omega is less than omega 3. So, therefore, this establishes the important fact that the anti-resonances may not necessarily occur between every two resonant peaks, between every two consecutive resonant peaks, right. So, we can make a simple thumb rule that closer the excitation and response DOFs, right, closer they are, the excitation point and response point for the FRF, then higher would be the number of anti-resonances, higher would be the number of anti-resonances, and farther they are, the response and excitation DOFs, smaller will be the number of anti-resonances, right. Another important point we should note is that anti-resonances, anti-resonant frequencies, they are not global properties of the structure of the system, right. Right, they are not global properties. This is because if we change either the excitation coordinate or degree of freedom, or the response degree of freedom, or both, then the intelligence frequencies would change, right. So they depend that where the structure is getting excited and where the response is collected, right. That is why they are not the global properties. However, if you look at the resonance frequencies, then resonance frequencies do not depend on the excitation and response degrees of freedom. Wherever the structure is excited and wherever the response is collected, the resonant frequencies of the system or the resonant peaks in the FRF would occur at the same frequencies. That is why resonance frequencies are global properties, right, of the system. Now the anti-resonance frequencies existence, it can also be exploited in the dynamic design. Anti-resonance frequencies can be exploited in vibration control, right, or the dynamic design. Okay. So let us say that a structure is being acted upon by force F, right, at let us say kth degree of freedom. So let us say there is a force Fk at frequency omega, is a harmonic force acting at k degree of freedom, right, and let us say Xj is the response at j degree of freedom, and let us say this Xj is very high and needs to be reduced. So what can be done, or one strategy could be, is we can assign or locate the anti-resonance frequency of the frequency response function alpha jk such that it is located at frequency omega, okay, at which the force is acting. If that can be done, then the response at j degree of freedom will be very small, okay, it can be made very small. So this is a strategy that can be used for vibration control. Let us now look at how we can estimate anti-resonance frequencies. So estimation of anti-resonance frequency. So we look at two methods, right. The first method is based on from the model. So if we have the model, then how we can determine the anti-resonance frequencies. So we see that we have the FRF expression. Let us say we are interested to know the anti-resonance frequencies for the frequency response function alpha jk. Then we can write the alpha jk as sum of, right, phi jr phi kr, right, omega r square minus omega square, and if there are n modes, then r varies from 1 to n, correct. So if you take the LCM, then what can we do is that we can express this right hand side as ratio of two polynomials. So we can represent the numerator as the polynomial p in omega square, and then we have in the denominator a polynomial q in omega square, right. So these are the ratios. So FRF can be expressed as ratio of two polynomials, and this is a polynomial of order n minus 1 in omega square, and this is a polynomial of order n in omega square, right. So now for an undamped system, the FRF magnitude would be 0, right, at anti-resonance frequencies. For an undamped system, the magnitude of the FRF, right, alpha jk omega, this magnitude is, this FRF is 0, right, for undamped system at anti-resonance frequencies. So if this condition is applied to the above equation, what we see is that this numerator polynomial should be 0 at anti-resonance frequencies, and therefore this polynomial now we can solve. We can solve this polynomial and find its roots, right. So we will get n minus 1 roots for omega square. Okay. So these roots, the positive real roots, right, they basically represent the anti-resonance frequencies. The rest of the roots can be discarded. The positive frequencies, positive real roots, they are basically the anti-resonance frequencies of the system, right. So therefore this method can be used if we have the model with us, that is the mode shape matrix and the natural frequencies. So let us look at the method based on the spatial model. Right. So we know that the frequency response function matrix is inverse of the dynamic stiffness matrix, right, and the inverse of dynamic stiffness matrix can be written as adjoint of Z divided by determinant of Z, right. That is how we can write it down. And what is adjoint of Z? That is nothing but the matrix of cofactors of matrix Z, right, divided by determinant of matrix Z, that already is there. Okay. And so therefore now if I focus my attention on, let us say, one of the FRFs, that is alpha j k, then on the right hand side also, then I would have to I will be having only the j k cofactor in the numerator, right. So I will have cofactor j k, right, divided by determinant of Z matrix. So now what is cofactor j k? Cofactor j k is nothing but minus 1 to the power j plus k into determinant of the matrix Z j k divided by determinant of Z, right. And what is Z j k matrix? Z j k matrix is the matrix obtained by deleting jth row and kth column of matrix Z, that is ZJK. Now if I want to know the anti-resonance frequencies, so at anti-resonance frequencies alpha j k omega is equal to 0, right. If the FRF is 0, then from the above expression we see that the determinant of Z j k should be 0. Okay. We can also write down this as k j k minus omega square m j k is equal to 0, isn't it? And now this basically indicates that there exists a corresponding eigenvalue problem, right, because when we solve eigenvalue problem, the determinant of the coefficient matrix has to be 0, right, and therefore the corresponding eigenvalue problem is k j k, let us say some vector y is equal to omega square m j k y, right. So this is the eigenvalue problem of a hypothetical system that is obtained by deleting the jth row and kth columns of the stiffness and mass matrix of the system. So if this eigenvalue problem has to be solved, the determinant kjk minus omega square mjk has to be 0, which is the basically the original equation we got right from the analysis. So therefore, if now I have the spatial model of the system, then I can solve this eigenvalue problem, okay, and then obtain the anti-resonance frequencies, right. So the solution of this gives anti-resonance frequencies. So the eigenvalues we get, only the positive real eigenvalues need to be taken, and those would represent the anti-resonance frequencies. Let us also briefly talk about the stiffness and mass lines. For the single degree of freedom system, we describe the concept of stiffness and mass lines, and these lines can also be defined for a multi degree of freedom, for the FRF of a multi degree of freedom system, right. However, formulating a relationship between these lines and system parameters will be very complicated, right, and that is why this concept of stiffness and mass line is not of much practical value when we have a multi degree of freedom system, okay. So this stiffness and mass lines though form a skeleton of the FRF, but as far as the formulation of relationship of these lines with the system parameter is concerned, it is not of much practical value because the relationships are likely to become very complicated. Let us now look at the characteristics of the FRF of multi degree of freedom dam system. Okay, and let us for the purpose of discussion, let us assume a multi degree of freedom system with structural damping. Okay, so let me sketch a typical FRF we may have, right, for a 3 degree of freedom system with structural damping. Okay, so let us say I have the FRF alpha 11 magnitude in decibels. So this FRF may look something like this. Right. So what we see is that the resonances and anti-resonances are now less sharp, right, as compared to the multi degree of freedom system and dam system FRF, right, and that is because there is presence of damping, which basically make the response to reduce at resonances and increase a bit at the anti-resonances. Now the FRF for a dam system, it consists of real part and imaginary part. So if we have the FRF alpha 11, then there is a real part of this FRF alpha 11, and then there is some imaginary part of this FRF alpha 11. And the real part and imaginary part, they vary with frequency, but there are no frequencies at which both these parts together become 0, right, and that is why for a dam system the anti-resonance frequencies do not have FRF magnitude 0, and that is why the methods we studied for estimating the anti-resonance frequencies from the model and the spatial model, the methods we studied for undammed system, they cannot be used in this case because FRF magnitude is not 0. However, a rough estimate of these anti-resonance frequencies for undammed systems can be found out by finding the anti-resonance frequencies of the corresponding undammed model. Uh, let us look at the real and imaginary parts of the FRF. Let us look at the plot of the real and imaginary part. So, for a let us say for the point FRF, this plot may look something like this. Something like this, right? And similarly, we may have the plot of imaginary part of the FRF, and that may look something like this. Right. In the single degree of freedom system, we saw that the real part of the FRF becomes 0 at the natural frequency, undamped natural frequency of the system. But for a multi-degree of freedom systems, the real part crosses the frequency line, but it does not cross the frequency line at the natural frequency exactly, right? So that is the one difference. Similarly, the imaginary part for a multi-degree of for a single degree of freedom system, it reaches to maximum value at the natural frequency, but for a damped system, the imaginary parts, they do not reach to the maximum value at the natural frequency. That frequency may be slightly different. Let us also look at now the Nyquist plot. So let us sketch the Nyquist plot. Let us say we are plotting here the real part of the receptance, and we are plotting the imaginary part of the receptance, right? And so this plot may look something like this. Just sketching it a typical plot. Something like this. So we see that in the plot there are now 3 loops. In the plot there are 3 loops, and these 3 loops are there because there are 3 resonance frequencies. There are 3 modes of vibration, and that's why there are 3 loops. Now in the single degree of freedom system, the Nyquist plot for the receptance when the damping was of hysteretic type, the Nyquist plot traced a circular trajectory. It was the part of a circle. But in this case, these 3 loops, they are not part of the perfect circles, right? They deviate from a circular trajectory, and that occurs because there are other modes which are also contributing to the response. Okay, so the plot of each modal contribution is a circular trajectory, but because the response is also contributed by other mode contributions, and that's why the these trajectories are no longer circular. So I think in this way today we have discussed the characteristics of FRFs of multi-degree of freedom systems of both undamped and damped systems. I think we can stop here. Thank you.